Good evening, everyone. I hope you are having a wonderful Wednesday. Happy Hump Day. Woo woo! If you are working in the working class field, you know today is half point and you have more days into your work week and then you will be done to enjoy your weekend. So I'm so happy that you're tuning in, joining me as of today. I want to first apologize to my Facebookers. I noticed that we stopped going live on Facebook. So what I did is I continued on YouTube some of the lesson and I cut it off. I cut it off early so that everyone can be on the same page. Because guess what? I want everyone learning on the same pace because we're all discovering and exploring algebra together. Okay, so I'm going to recap a couple of things of of the last few things that I taught yesterday, and then we're going to continue on with the lesson plan. Okay, so before I do that, please send me a thumbs up, a like, a heart, all that good stuff to let me know that you can hear me so we can get started. Thank you so much. Let's get started. So yesterday we were covering roots and how to solve radical expressions and all that good stuff. And so I want to go back over the radical expressions that we did yesterday. So we had the last one I think we had before Facebook got cut off was square root of 16 p to the 8th and q to the 7th. Now, if you remember yesterday that each term are being multiplied to each other. So if they are being multiplied into each other, you can separate them into their equal parts or equal radical signs. So because I multiplied these two, I can go square root of 16 times the square root of p to the 8 times the square root of q to the 7th. Now remember, unless it's denoted as a plus or minus or a minus, the square root of 16 is a positive square root of 16. So therefore your answer is going to be a positive 4 times square root of p to the 8 which can also be changed into p to the fourth raised to the second power. And of course, the square root of that square is p to the fourth. Then we have the square root of q to the seventh, which when you break it down, it could be broken. If you remember yesterday, if it's an even or odd, you take one of them out and then break it down to the lowest term. So q to the seventh is q to the 3 raised to the second power times q. And the reason I did it that way is because the power rule says that an exponent raised to an exponent can be multiplied to each other. So q to the third raised to the second power is the same as saying q to the sixth. Broke those into two parts. And of course, you have times q. So q to the sixth times q gave me my q to the seventh. Okay? So once I take the square root of both of those, that leaves me with a q to the third on the outside and a square root of q on the inside. Because the only way that q can cancel is if it was q squared. But since it's q to the first under a square root, it must remain under the root. So once I find all my answers, I can combine my terms or multiply them back together to give me 4 times p to the 4 times p to the fourth times q to the third and the square root of q. And that is my final answer. Next, we did the simplified quotient, which allows you to simplify your numbers or simplify your letters or do both when you have a fraction under the radical sign. So the square root of 27 over 3. Well, of course, 27 over 3, that is the square root of 9, because 27 over 3 is 9, or 27 divided by 3 is 9. Therefore, the square root of 9 is 3. Now, say for instance, you have a fraction that is not evenly divided, but you have two perfect squares, such as the square root of 9 over 16. Well, based on the simplified quotient rule, you can separate the square roots from each other to their own radical signs. And the square root of 9, that gives me 3. And the square root of 16, that gives me 4. So my answer of the square root of 9 over 16 is 3 over 4. Now, square root of, say for instance, the number you have, one or both of the numbers you have cannot be evenly distributed as a radical in the denominator. So say for instance, you have the square root of 9 over 2. Well, that can be broken down, of course, into square root of 9 over the square root of 2. Now we know that the square root of 9 is 3, but the square root of 2 remains a square root because it is not rational. It's irrational, meaning if I take the square root of it, The, the decimal will not repeat and the decimal will not stop. Therefore, it remains a radical. So, whenever you have a radical sign or a root sign in the denominator, you must get rid of it. There can't be zero or it's undefined, and there can't be a square root or any root in the denominator for it to be considered the fraction. So, how do we get rid of the square root? Well, we rationalize our square root by multiplying the square root of 2, top and bottom, to our answer. And 3 times the square root of 2, that gives me 3 square root of 2. And of course, the square root of 2 times the square root of 2 is 2. Because square root of 2 times square root of 2 is square root of 2 squared. And of course, when the roots cancel, that leaves the number on the inside. So whenever you multiply the same root to itself, the roots will cancel. Therefore, you should have a whole number. So your answer to the square root of 9 over 2 is 3 square root of 2 over 2. Any questions on simplifying the quotient with numbers? All right, moving on. Of course, what you can do to numbers, you also can do to letters. So how can I do to numbers as I've done to letters? So you have the square root of, say for instance, you have x to the 4th over x to the 2nd. If they're the same, you can subtract their exponents, which when you're dividing a variable over the same variable but different exponent, you can subtract the exponents, which the square root of x to the 4th over x to the 2nd becomes x to the 2nd. Why? Because x to the 4th over x to the 2nd can be written as x to the 4 minus 2. That's how I got the square root of x to the 2nd, or x squared. So once I find that answer, then of course the square root of x squared, the squares cancel, the square and the root cancel, and my answer is x. Now, what if I have 2 different variables? Well, just like 2 different variables with 2 different numbers, if it can be evenly divided based off the root, it can be pulled out. So you have the square root of x to the 4th over y to the 4th, which of course will give me the square root of x to the 4th over the square root of y to the 4th, which turns out to be the square root of x to the 2nd raised to the 2nd power over the square root of y to the 2nd raised to the 2nd power. Once I find that answer, the square on the outside and the root cancel, and that leaves me with x squared over y squared. Now, what happens if there's a radical in the bottom with my denominator, and it's just letters. The same rule applies if it was just numbers. You must rationalize your denominator. So say, for instance, I got the cube root of x to the third and y to the fourth. Better yet, I'm going to try a different way. Y to the second. So now we are dealing with the cube root. So you have the cube root of x to the third, and you have the cube root of y to the second. So cube root of x to the third, of course, those cancel, and that gives me x. But the cube root of y squared is still going to be the cube root of y squared, because you cannot pull a cube out of a square. Therefore, you have the cube root of y squared. So to rationalize, I multiply by the cube root of y squared on the top, cube root of y squared on the bottom, and my answer leaves me with x cubed root of y squared over y squared. Because when you multiply a root to a root, it's the answer on the inside. Any questions on rationalizing and simplifying quotients with numbers and letters? All right, next I'm going to touch back on something that was not covered but definitely needs to be covered, because you're going to see it when you're doing your homework. So this is called the quotient of two trinomials. That is when you're dividing a trinomial by another trinomial. And so to do that is usually called simplify, and you simplify a trinomial that's divided by another trinomial. So you have x squared plus 2x minus 3 on the top, and you have x squared plus 7x plus 12 on the bottom. So to simplify this, you must factor the top and factor the bottom. So to factor the top, of course, simple factor says what multiplied together gives me a -3. What subtracted from each other gives me a +2. Well, a +3 and a -1 multiplied together gives me a -3. A +3 minus 1 gives me a +2. Therefore, when I factored my x squared plus 2x minus 3, it gives me x plus 3 times x minus 1. All right, moving on to x squared plus 7x plus 12. So if I have plus plus, that means I'm going to have two plus signs. I break down my x's as x and x because x times x is x squared. So what multiplied together gives me 12. What added together gives me 7. Well, the ordered pair that multiplies together that gives me 12 and added together that gives me 7 is 4 and 3. Because 4 times 3 is 12. 4 plus 3 is 7. So now that I have factored out my numerator and my denominator, I can therefore eliminate or simplify by crossing out the top one to the bottom one if they are like terms, meaning if they are like binomials. So if I have an x plus 3 on top, I can cross it out if there's an x plus 3 on the bottom. That's just like saying if I have 2 to the 4th times 5 to the 2nd. I can easily cross the 2 out on the top and the 2 out on the bottom, and that'll leave me with 5 over 4. But there must be a like term in the numerator as well as the denominator in order for them to cross out. If they're both on the top or both on the bottom, they cannot cross out. They just multiply into each other. So once I cross that out, what I'm left with is x minus 1 over x plus 4. Another example, we have x squared minus 2x minus 8, x squared minus 5x minus 14. Break these down. You have x, and of course this is going to be plus and minus, because minus minus gives me a plus and minus. So what multiplied together gives me a negative 8. What subtracted from each other gave me a negative 2. So just in case you don't know the factors of the factored pairs of 8, here they are. You have 1 and 8, 2 and 4. That's it. 1 and 8, 2 and 4. So now 8 minus 1 is 7. 4 minus 2 is 2. So my 2 will go here and my 4 will go here. The reason why the 4 is the minus is because my middle term is minus. Remember, the middle term will determine with a plus or minus if the bigger number is going to be positive or the bigger number is going to be negative. If the middle term is positive, the bigger number is positive. If the middle term is negative, the bigger term is negative, or bigger number is negative. Okay. Next we have x squared minus 5x minus 14. So now I have an x plus x minus. What multiplied together give me 14. What subtracted from each other gives me a negative 5. So we know that the pairs for 14 are 1 and 7, 1 and 14, and 2 and 7. Sorry about that. So now 14 minus 1, that's 13. 7 minus 2, that's 5. So that means my bigger number goes in with the negative, and my smaller number goes in with the positive. And of course, the binomials, those are top and bottom, they cancel. And what I'm left with is x minus 4 over x minus 7. Any questions? All right, moving right along. Multiplying radicals. What does that look like? What does that feel like? What is it? Okay. You remember how we could split the radicals up if they're on the inside because they're multiplying to each other, and you simplify them? Well, you can multiply them. So, say for instance, I have 6 cube root of 9n squared times 3 cube root (24 times n), or 24n. Now, remember, these numbers that are on the outside of the root are multiplying to the root. Therefore, you can multiply the numbers on the outside to each other, and you can multiply the numbers on the inside to each other, as long as the root is the same. And here's how. You have 6 times 3. That gives me 18. Cube root, you have 9 times 24. That gives me 216. So 9 times 24 on the inside of the radical gives me 216. Then n squared times n, that is n to the third. So now I can break it down and simplify it by going 18 times cube root of 216 times the cube root of n to the third. So now the 18 you bring down, and you take the cube root of 216, which is 6, because 6 times 6 is 36. 36 times 6 is 216. Then you take the cube root of n to the third. Well, a cube root to a cube cancels, and that leaves you with n. Therefore, your answer is 108 n. Here's another example. You have the square root of 2ab squared times square root 6a to the third b squared. Of course, multiply the numbers to each other under the radical, And 2 times 6 gives me 12. A to the first times A to the third. That gives me A to the fourth. And of course, B squared times B squared is B to the fourth. Once I find that answer, then I can begin my simplifying process. So now I can break these down into 3 terms of the square root of 12 times the square root of A to the fourth times the square root of B to the fourth. Now the square root of 12 has a perfect square in it. The perfect square inside of 12 is 4. So the square root of 4 times 3 is how you would break down 12. You're always looking for a perfect square. So it must divide by 1, 4, 9, 16, 25. Usually the first 10 perfect squares in order for it to be considered for you to be able to rationalize the number. So the perfect square within 12 is 4. And of course, 4 times 3, that gives me 12. So I've already started my pullouts. Next, of course, square root of A to the fourth can be rewritten as A to the second raised to the second power because 2 times 2 is 4. And the same goes for square root of B squared raised to the second power because 2 times 2 again is 4. So now the square root of 4 times square root of 3. If you're a skip stepper like me, I would simply just say 2 square root of 3. But of course, if you like it broken down all the way to see how that comes about, you have the square root of 4 times the square root of 3 times the square root of A squared to the second times square root of B squared to the second. So then the square root of 4 is 2. You'll leave 3 on the inside, which will give you square root of 3 times square root of A squared to the second is A squared times B to the second, or B squared to the second is B squared. Once you take the square root, and if I write my answer in order, it's 2A squared, B squared, square root of 3. If you notice, the radical always goes on the end. You want to make sure that your radical sign is always going on the end. Any questions? All right. We are moving on to adding and subtracting radicals. So, say if you have the radical of 2 square roots of 3 plus 3 square roots of 3. The rule of adding and subtracting means all you have to do is add and subtract the number on the outside. So, you have 2 plus 3. That gives me 5 square roots of 3. Same rule applies if you have 4 square root of 5 minus 2 square roots of 5. That will give me 2 square roots of 5. Now, what if you do not have like radicals? Just like if you didn't have like fractions, how would you break that down to make them alike? And is it possible for them to be alike? Well, here's an example of what that looks like. Say, for instance, you are asked to simplify 2 square root of 12 minus 3 square root of 27 plus 2 square root of 48. Now, remember I said you should be able to pull a perfect square out of each of these functions. And the only way you can do that is by going through each one. So, first thing we need is to find the perfect square in 12. And of course, the perfect square in 12 is 4 minus 3. And the perfect square in 27 is 9, because 9 times 3 is 27, and the square root of 9, that is 3. Therefore, the perfect square inside of 27, that's 9, plus 2 square root, the biggest perfect square in 48, you would think would be 4, but it's really 16. And of course, you would say 16 times 3 in order for you to get your perfect square that's getting ready to be pulled out and the number to have under the radical sign. So now, pulling out my squares, I have 2 times 2 square root of 3 minus 3 times 3 square root of 3 plus 2 times 4 square root of 3. And of course, you multiply your terms that are on the outside. And that gives me 2 times 2, that is 4 square roots of 3, minus 3 times 3, that is 9 square roots of 3. And of course, plus 2 times 4, that is 8 square roots of 3. And of course, from left to right of order operation, 4 minus 9, that gives me a -5. -5 plus 8, that gives me a positive 3 square root of 3. Any questions on adding and subtracting and simplifying like and unlike radicals? Now, say for instance, you still had your 2 minus the square root of 12, and you had your minus 3 square root of 7, but your last term is 2 square roots of 5. Well, these two still break down the same. The first two terms still break down the same. And of course, 2 square roots of 5 is in its simplest form, so you have to do nothing to it. So now, 2 times square root of 2, square root of 4 is 2. So that'll give me 2 square roots of 3 minus 3 times 3 square roots of 3, because the square root of 9, that gives me 3, plus 2 square root of 5. Then I have 4 square root of 3 minus 9 square root of 3 plus 2 square root of 5. If one of your radicals are not the same, you cannot add them, you cannot subtract them. Pretty much you have to treat it like if it was x plus y. What does that mean? 4 minus 9, that is a negative 5 square root of 3 plus 2 square root of 5. That is your answer. You can't break it down any further. You can't combine them into each other because the radicals are not the same. Therefore, you have a minus 5 square root of 3 plus 2 square root of 5. You can also rewrite it as 2 square root of 5 minus 5 square root of 3, just in case you want the positive number in front of the negative number. Either way, you cannot combine them because they do not have the same radical sign. Any questions on that? All right. What does it look like to multiply a binomial radical? What does that look like? How do we solve it? All that good stuff. All right. Say for instance, have square root of 5 minus the square root of 3 times 2 square roots of 3 plus square root of 2. How you multiply these are FOIL. First, square root of 5 times square root of 2 times 2 square roots of 3. That will give me 2 square roots of 5 times 3. Next is outer, which is my first term in the first parenthesis times my second term in the second parenthesis. So now, square root of 5 times square root of 2 is plus square root of 5 times 2. Now, keep in mind, if it's on the outside, if the number's on the outside, you multiply the numbers on the outside together. If it's on the inside, you multiply the numbers on the inside together. Next, we have inner, which is the last term in the first parenthesis, the first term in the last parenthesis. So now you have minus 2 square root of 3 times 3. And finally, last, which is minus square root of 3 times 2. So, combining all the terms, inside, outside, indifferent, combine your terms based on multiplication, then on addition and subtraction. So first thing we'll do is bring down my 2 square root. That gives me 15 plus square root of 10 minus 2 square root of 9 minus square root of 6. After that, you have 2 square root of 15 plus square root of 10 minus 2 times 3, because square root of 9 is 3, minus the square root of 6. And when I get rid of all of these terms, well, combine my terms again, you are left with 2 square root of 15 plus square root of 10 minus square root of 6 minus 6. This is your answer. And unless you have a perfect square to pull out of any of these numbers, this is where you will stay. Of course, if there was more multiplication, you can multiply things together and add them together if they were the same. But since they are not, this is your answer. Your answer is just like this. Consider this like when you multiply a binomial to a binomial, you ended up with your trinomial. Same process. You're foiling. First, outer, inner, last. Any questions on multiplying radicals? Now, there's another thing you must do, because of course, remember, radicals cannot be in the denominator. So what if you have 1 minus the square root of 3 over 5 plus the square root of 3? Well, you could multiply everything by the square root of 3, but the problem is there's a 5 being added to that square root of 3. Therefore, in order to rationalize the denominator, you multiply with what they call the conjugate, which is if there's a 5 plus the square root of 3, you must multiply with a 5 minus square root of 3. And the reason you do it like that, you remember a rule we got called difference of squares? That's where this comes in. So you have 1 minus the square root of 3 times 5 minus the square root of 3. And of course, based on our formula, where the two conjugates multiply into each other, you should have 5 squared minus square root of 3 squared. Sidebar, in case you forgot what this was, the formula says if A plus B is multiplied to A minus B, then A squared can be subtracted from B squared. That's how I came up with this. So now, moving on. On the top, we have FOIL. 1 times 5. That gives me 5. 1 times the square root of 3 is minus square root of 3, because that is a negative square root of 3. Then you have the square root of 3 minus square root of 3 times 5. That is a minus 5 square root of 3. And of course, minus square root of 3 times minus square root of 3. Of course, square root of 3 is multiplied to each other, and negative to negative makes positive. Square root of 3 times the square root of 3. That gives me 3. Because, of course, square root of 3 times square root of 3 is square root of 9. Therefore, the answer is 3. Or, of course, square root of 3 times square root of 3 equals the square root of 3 squared. That also will give me 3. Now, to the denominator. 5 squared, 5 times 5, that gives me 25. Minus the square root of 3 squared. That gives me what? 3. So now, combine like terms. On top, you have 5 plus 3, because those are whole numbers without radicals. Therefore, 5 plus 3, that is 8. Then you have a minus square root of 3 minus 5 square roots of 3. Well, of course, if there's no 1 in front, if there's no number in front, it's understood as a understood positive or negative 1. So minus square root of 3 minus 5 square roots of 3. Like terms, you add, which gives me minus 6 square roots of 3. And of course, 25 minus 3, that gives me 22. Now, if you want to simplify it further, you can divide everything by 2, because with fractions, of course, you can simplify by dividing everything by 2. So if I divide everything by 2, that leaves me with 4 minus 3 square root of 3 all over 11. I will accept this or this answer, depending on what the question asks. If the question says completely simplify to the lowest term, this would be your answer. If the question just simply says simplify or use a conjugate to rationalize a denominator without saying simplify to the lowest term, this will be your answer and it is acceptable. Any before we move on from conjugating rational denominators? All right, moving on, we have rational exponents. Remember, exponents are typically raised to a whole number power. So you might have 2 to the 4th, or x to the 5th, or c to the 3rd, d to the 8th. That is considered a whole number exponent. Now, when you have rational exponents, rational exponents simply means you have fraction exponents. So that means that it's 2 to the 1/2, 3 to the 2/3, x to the 4/5, or y to the negative 2/8. So now, what does all of that mean? Well, whenever you have a radical and is raised to a fraction exponent and your fraction numerator is 1, that simply means that your root is the denominator. So your roots are always the denominator. Your power, or what the number is being raised by, is the exponent. This is what I mean. So to simplify, 2 to the 1/2. 2 to the 1/2 is 2 raised to the first power, and the half root. So, well, the half exponent, or the square root, because the half exponent is the square root of 2 to the first, which gives me the square root of 2. Next, we have the 3 to the 2/3. Well, 3 is being raised to the second power, and that is being raised to the 1/3 power. So 3 squared raised to the 1/3 power. The third is your root. The square is your exponent. So 1/2, that's 1 times 1/2. 2/3, that is 2 times 1/3. So now the third exponent becomes the cubed or third root of 3 raised to the second power. And of course, 3 raised to the second power under the cube root is the cube root of 9. Now, this will remain the cube root of 9 because 9 is not a perfect cube. Now, the same thing that you did for the numbers, you must also do for the letters. Now, I did a negative one and a positive one because, and I'm also going to change this to a negative 2 to the 7th. Do it like that. So now, x to the 4th fifths is simply x to the 4th raised to the 1/5 power. And of course, the 1/5 power is the 5th root. And that 5th root is of x to the 4th. And of course, the 5th root of x to the 4th is still the 5th root of x to the 4th. You cannot rationalize it out or simplify it because there is nothing to the 5th that can be pulled out of to the 4th. Now, if you have a negative exponent, if you remember, if it was a whole number, like 2 to the negative 2, that could be flipped to 1 and 2 to the second. And that, of course, becomes 1/4. If you have 2 to the negative 1/2, that is 1/2 to the 1/2, which of course is 1 over the square root of 2 multiplied by the square root of 2 because the square root of 2 cannot be in the denominator. And that leaves me with the square root of 2 over 2. So what you do with the number, the same rule applies when you do it with the letter. So you have y to the negative 2 over 7. You can do this 2 ways. So, first way is you have y well, 1 over y to the 2 over 7. And of course, that will leave you with 1 over y raised to the second to the 1/7. And of course, that gives me 1 over the 7th root of y squared multiply 1 over the 7th root of y squared to the 7th root of y squared, top and bottom. And that leaves me with the 7th root of y squared all over y squared. Another way of doing this is, say for instance, you have y to the negative 3/4, which of course, when you flip it, is 1 over y to the 3/4. Of course, based on the radical signs of making the fractions whole, you can multiply y to the 4th on top and y to the 4th on the bottom. Now, the reason why you can do that is because, of course, 3/4 plus 1/4, that gives me 4/4, or y to the 1st, and 1 times y to the 4th is y to the 4th. And of course, that leaves me with the 4th root that number's still too big. That leaves me with the 4th root of y over y. Any questions before we move on? All right. Moving on, we are diving into complex numbers. So, you guys remember when I said you cannot take the square root of a negative number because it's not a real number. Well, there is a math system called the complex numbers because the square root of a -1 is an imaginary number. So it can be denoted as the letter I. So the square root of -1 equals an imaginary number, which is also the complex number, which is the system of I. So for those who wanted to know, okay, how do I solve the square root of -1 and you're no longer dealing with real numbers? So if we're only dealing with real numbers, there is no real number that'll get real number for the square root of -1. But if we are dealing with the complexity of the square root of -1, we realize that it's -1 as a square root is an imaginary number. Therefore, the system of I was created and born. So the imaginary unit is I. You'll see it as I, 3I, 1 minus I, or 2 plus I. You may even see I square root of 2. Those are one of the many forms you will see of the imaginary unit. Now, say for instance, I want the square root of -4. Well, the square root of -4 can be broken down into the square root of -1 times the square root of 4. And of course, the square root of -1, that's I, times the square root of 4, that's 2. Therefore, the answer is 2I. Another example would be the square root of -x to the 4th. And of course, let's make this even more interesting. Sorry about that. Square root of -9 x to the 4th. So, of course, you have the square root of -1 times square root of 9 times the square root of x to the 4th. Square root of 1 is I. Square root of -1 is I. Square root of 9 is 3. And of course, the square root of x to the 4th is x squared. And so my answer is 3I x to the 2nd. Now, say for instance, that was x to the 3rd instead of x to the 4th. Well, the square root of x to the 3rd is x square root of x. Therefore, my answer is 3ix square root of x. And of course, if the number had been any different, the number would have remained on the inside, such as 5 or 7 or 13 or 10, because there's no perfect square in 10. So always remember, if you can't take the square root, it will remain under the square root. If you can't take the cube root, it will remain a cube root. If you can't take any roots, what is left inside will remain a root. So what does it look like when you multiply imaginary numbers? Well, you have, first things first, know that the square root of -1, that's I. So I squared is -1. Then I to the third. Well, of course, if you have I to the third, that is I squared times I. So that is -I. And of course, I to the fourth is a +1. Now, the reason why I to the third is -I, well, we know that I is the square root of -1, and those are interchangeable. Then you have I squared, which is -1, and those are interchangeable. So all I did was take a -1, times it to I, and that's how I got my -I for I to the third. Any questions of these breakdowns? All right. So now, multiplying imaginary numbers. Say, for instance, you have a -2I times 7I. Well, -2 times 7, that's a -14. I times I is I squared. And we know that I squared is -1. Therefore, the answer is 14. What if you have a radical? Say, for instance, you have the square root of -10 times the square root of -15. Well, of course, if I pull out my negatives, that'll be I I square root of 10 times I square root of 15. Of course, I times I, that gives me I squared times the square root of 150. I squared is -1 times a perfect square inside of 150 is 25. And you have 6. I still keep going. So now equals -1 times the square root of 20. Well, of course, the square root of 25 is 5. Then, of course, and the square root of 6 is still the square root of 6. So therefore, that becomes 5 square roots of 6. And -1 times 5 is a -5 square root of 6. Any questions on multiplying your imaginary numbers? Next, we have simplifying the power of your imaginary numbers. So remember my I squared, I to the third, I to the fourth. These come in handy for when you're trying to break down your answers for simplifying a power of I. So say for instance, you have I to the 45th. This can be broken down in so many ways. For me, because I know that I can separate I to the 45th into I to the 44th times I, because of course I to the 44th times I to the first is the I to the 44 plus 1. And that's why I was able to break down 45 to I to the 4th times I. So if you remember, I to the 4th is 1. So 44 is a factor of 4. So I can say I to the 4th, and I multiply that times and raise that to the 11th power. That gives me my I to the 4th to the 11th power, or I to the 4 times 11. That's how you get I to the 44. And still you multiply that I. So now, I to the 4th, we remember, is 1. Because I squared times I squared. -1 times -1 gives me 1. 1 to the 11th times I. And of course, 1 to any power is 1 times I. Therefore, your answer is I. Now, you can break these down however you prefer. You can split them in half to where you had I to the 22nd times I 22nd times I. That still would have been the same. You still would have came up with the same answer. Always know that you can break your numbers down simply by shifting them into their known forms. Also, I to the 45th could also be broken down into I to the third. Could I do that? Let's see. I to the third raised to the 15th power. Let's see. Can I get away with that? I to the third raised to the 15th It'll still be where I have to do negative I to the 15th. And of course, once you raise that to the 15th power, you break those down into yeah, still gonna be the same answer because I'll still end up with, once I raise that to the 15th power, that still is gonna give me I, which is what I found in the first place. So, any questions before I move on to the next problem? Now, what if you have an equation with an imaginary solution? Here's how you solve this. So, say for instance, you have 3x squared plus 48 equals 0. Subtract 48 on both sides. That gives me 3x squared equals a negative 48. Divide both sides by 3. And x squared equals a negative 16. Of course, if you have this type of x squared, that means you should have two answers. So that is going to give me, because I'm going to take the square root of both of these on both sides. So square root of x squared, that's x. And of course, you should have two answers. Therefore, you should have a plus and minus square root of negative 16. Once you find that, x should be equal to plus or minus, where we know the negative is going to give me I, and the 16 is going to give me 4. Therefore, my answer is the square root of plus or minus 4I. Any questions before we move on to adding and subtracting, multiplying and dividing complex numbers? All right, moseying along, we have, if you remember how you added and subtracted the radicals, it's the same process when you add and subtract imaginary numbers. You combine imaginaries to imaginaries, and you combine real numbers to real numbers. What I mean by that is, say for instance, I have 6 minus 4i plus 1 plus 3i. Combining like terms tells me that I can do 6 plus 1, and that gives me 7. I also can say minus 4i plus 3i, because it's just like if you had 2x plus 3x, that of course gives me 5x. The same rule applies with the i's. So I have a negative 4i plus 3i. That is going to leave me with a negative I. Another example with subtraction, you have 3 minus 2i minus 5 minus 4i. And of course, 3 minus 5, that gives me a negative 2. And minus 2i plus 4i, because minus and minus makes plus. Minus 2i plus 4i gives me a positive 2i. Any questions on adding and subtracting complex numbers? All right. Multiplying complex numbers. Say, for instance, I have 1 plus 3i, and I multiply that to 7 minus 5i. Of course, you will do the FOIL method, which says first 1 times 7, which is 7. Outer 1 times a negative 5i, that's minus 5i. Inner 3i times 7 that gives me a positive or plus 21i. And of course, 3i times a negative 5i, that's a minus 15i squared. So now, combine these like terms, and I bring down my 7 minus 5i plus 21i, 21 minus 5, that should be 16. Because 16 plus 5 is 21, therefore 21 minus 5, or minus 5 plus 21, still gives me a positive 16i. Now, you have a minus 15, but you also have to remember that minus 15 is multiplied to I squared, which of course we know that I squared is negative 1. And of course, have 7 plus 16i plus 15, because negative and negative makes positive. Therefore, you have a 22, because 15 plus 7, that's 22, plus 16i. Last but certainly not least, we have dividing complex numbers. So, of course, just like radicals, just like zero, imaginaries cannot be in the denominator. So to solve, you must either find the conjugate or multiply by I to get rid of it. Here's what I mean. First example is 5 plus I all over 2I. Now, in order to get I out of the denominator, you must multiply the top and the bottom by I. So now you have I times 5 plus I all over 2 times I, which is 2I squared. Of course, you know, if I distribute my I, that's going to give me 5I plus I squared all over 2 times a negative 1, because I squared, of course, is still negative 1, equals 5I plus negative 1 all over negative 2. And of course, you have negative 1 plus 5I all over negative 2. And that can be broken down into 1/2 plus, no, correction, so that's negative, because both of them are over 2. Negative makes positive, so that's 1/2 minus 5 over 2, that is 5 over 2I. Now, say for instance, you have a plus or a minus conjugate for your complex number. Here's how you would solve it. Example 3I, 2 plus 4I. Conjugate of 2 plus 4I is 2 minus 4I. And of course, what you do on the bottom, on the top, what you do on the bottom, you must do on the top. So now you have 3I times 2 minus 4I all over, difference of squares still applies here. So you have 2 times 2, that's 2 squared, and minus 4I, 4 times 4, of course, that's 4 squared, and I squared. Or another way you could have written it was 4I squared. Whichever, but know that when you're squaring the I, you're also squaring the 4. So, distributive property of the denominator says 3I times 2, that gives me 6I. 3i times a negative 4i, that's a minus 12i squared. Then, of course, 2 squared, that gives me 4, minus 16i squared. 6i minus 12 times a negative 1. I squared is still negative 1. 4 minus 16 times a negative 1, because I squared, of course, is still negative 1. And what you are left with is 6i plus 12 over 4 plus 16 which leaves me with 12 plus 6i all over 4 plus 16, that gives me 20. So now you know that 12, 20, and 16 has what number in common? 2. So now everything can be divided by 2. Or you can split them apart, such as 12 over 20 plus 6i over 20. And if you do it like that, simplifying your fraction, 12 over 20 becomes 3 over 5. Wait. Yep, because 4 divided by 3, 12 divided by 4 is 3, 20 divided by 4 is 5, plus 6i over 20 becomes 3 over 10i, because 6 will go into 2 3 times, and 20 will go into 2 10 times. So your final answer is 3/5 plus 3 over 10i. Also, this is known as the standard form of your complex number. Any questions on complex numbers? Well, you guys, that's all I have for today. So I want to first say thank you for tuning in, and thank you so much for joining me on today. I asked for a better class. Of course, you guys, if you have any questions outside of the live, you can inbox me, you can DM me, you can IM me on all of my social media platforms, which are on Facebook for Krishan McConaughey, or you can find me under Mathematics for You Tutorial Services, LLC, for Facebook and YouTube. Of course, the YouTube and the Facebook pages links are listed in the description of each video, so you can always click, rewind, and review once the live has ended. Do we have any questions before we end? Checking my Facebook. Hi, everyone on Facebook. Checking YouTube. Hello, everyone on YouTube. Thanks for tuning in. Well, if you guys have no questions, I am going to go ahead and end our live. Of course, you can IM me, DM me, or inbox me on my Facebook and YouTube pages. Links are below in the description, or you can text me at 205-542-5062, 205-542-5062. Again, I thank you so much for tuning in. I'm glad you guys were able to enjoy everything that I'm teaching. And I thank you so much for sharing and learning with me as we discover and explore Algebra 2 together. So, since there are no other questions, Miss Chris will leave you to rewind and review for those who have to. Otherwise, thank you for joining me this wonderful Wednesday. Make sure you get over the hump of today because guess what? It's 2 more days to the weekend, guys. And I will catch you on Friday. At what time? 5 p.m. So, see you guys on Friday. I look forward to hearing from you. Thank you for tuning in with Miss Chris of Mathematics for You Tutorial Services LLC, where we are changing mindsets one problem at a time. Have a blessed evening, darlings.